So moving into chapter 6, imagine something, like a long string or something stretched, here, and you're holding one end of it right here. Okay, so here you are holding one end of it, and you move your hand up and down in harmonic motion. So you move your hand up, that pulls up this end of the spring, or the string. Now that is providing a tension that pulls this part up, and then your hand goes down. So then you have a bump right there. Okay, and then this pulls this part up, and so it looks like that, but now you're pulling down here, but then your hand goes down. And so then this goes up, and then like that, and then like that, and so what happens is that you get a harmonic wave. So a harmonic wave would look like a sinusoidal wave of this sort. And so in discussing the sinusoidal waves, then we're going to say the wave is moving at a certain speed, okay, and the way I was drawing it, the wave was going this way. It doesn't really matter if it's going to the left or to the right, so you can have a wave going this way, it looks the same way, okay, and so if you're standing here watching the wave go by, then if you're watching one little spot on the wave, that little spot goes up and down like that. Okay, even though the wave, a fraction of a second later, the wave looks like it's here, and then it looks like it's here, and then it looks like it's here. Okay, so the wave looks like it moves from there to there, okay, as this is passing, but each little spot on the wave just goes up and down. And so we would say that this distance from one peak of the wave to the other we call a wavelength. Okay, now that wavelength should be the same wherever you measure on the wave. So if you measure from the midpoint going up to the midpoint going up, if you measure from the trough to the trough, the peak to the peak, 2/3 of the way up to 2/3 of the way up, like almost to the bottom to almost to the bottom, this should always be the same number if this is in fact a harmonic wave. A harmonic wave, because the motion is going up and down sinusoidally, then that means that you can describe this wave as a sine function or a cosine function. And so the symbol for wavelength is a lowercase Greek lambda. So that's our symbol for the speed of the wave. So let's say the wave's going this way now. So the speed of the wave is basically going to be how long it takes for this peak to reach the position of the other peak. And so the speed, and I'm going to actually use a little bit different terminology than your book. I'm going to use the letter C for wave speed. So now the reason I don't use V for wave speed, because your book uses V for wave speed, I reserve V for the speed at which something's going up and down. Okay, that's not necessarily the same as the wave speed. And so the wave speed is going to be the wavelength divided by the period, the time it takes for this piece to go down and then back up. Okay, that's going to be how long it takes for this wave to go do this and then to do that. So this piece is going down, and then keep going until the piece is all the way to the bottom. Okay, and then it starts going back up again until it's back at the top. That's the period. So the wave speed is lambda over period. Well, we know that 1 over period is frequency, so we can say wave speed is wavelength times frequency. Now, notice this does not in any way, shape, or form be affected by by whatever it's waving. Okay, because we could also have like a pressure wave. So we have air pressure, and then you blow and you make high pressure, and then it's low pressure, and then this high pressure expands, and now you have high pressure here, okay, and then that moves, and then you have high pressure here, and then this is high pressure over here. So what you have is a wave in which you have high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. If you made a graph of pressure, it would look like that. Okay, so this is going to be, pressure, versus position. Okay, and so now this looks exactly like the other kind of wave. So in this case, the air molecules are moving back and forth some velocity v, but this high pressure region is moving some velocity c. So that this velocity is not the same as that velocity. So these things are going back and forth as the wave is moving. And so you end up with a little bit more complicated sort of scenario right there. And so this type of in which the motion is back and forth this way while the wave's moving. So these are like these pressure waves. This would be like sound waves. Okay. That is what we call a longitudinal wave. Now, if instead everything is moving perpendicular to the direction the wave is moving, we call that a transverse wave. Now, there are other kind of waves that are out there, but these are the two main types we're going to be worrying about right here. And so they both can be described in the same fashion. But again, they both get down to this idea that the speed of the wave is equal to the wavelength times the frequency. That equation will actually hold for all kinds of waves. And in physics 2, we're going to talk about electric and magnetic fields. So we're going to talk about a wave here that has electric field up, electric field down, electric field up, electric field down, and a magnetic field, for example, out of the board or out of the page or into the page or something like that. That's an example of a wave. Okay, we can also have matter waves. A fellow named Schrodinger was able to describe the wavelength of electrons in a atom. A fellow named de Broglie actually originally had come up with the idea that waves, that particles can have waves. Prior to him, they'd shown that, for example, that light acts as both particles and waves, and so you can measure from the wavelength of light, you can find the momentum of light, and so that'd be acting like a particle. And de Broglie showed that, well, if something is moving, so if it's a particle moving, it's going to have a wavelength. And so from that, Schrodinger was able to incorporate that idea into the ideas of atoms, and with a Schrodinger equation which describes the energy states of atoms. So those would be matter waves. And all of them basically have the same basic concept, and that is that the same equations hold for all different waves. So once you learn waves in one form, you learn waves in all different other forms.